Welcome to the second lecture in magnetostatics and 19th lecture for Physics 4B. We continue our introduction of magnetism, finally introducing how magnetic fields are produced using objects that are more fundamental and simpler than permanent magnetic dipoles. So, we start by introducing Biot-Savart's law, highlighting the similarities with and the differences to the Coulomb's law, the counterpart to the Biot-Savart's law in electrostatics. As mentioned earlier, just even to state this basic law of magnetism, we need to use vector cross product. So, if you don't yet feel comfortable with the right-hand rules, I strongly recommend reviewing them. We covered the right-hand rules in the last lecture, lecture 18, and in the earlier vector lecture, lecture 9 in this class. It's in magnetism where we use these cross products so much that some intuitive feel for the overall result is helpful. This intuition is captured in the shortcut right-hand rules that we cover as we look at the directions of magnetic fields for a straight line of current and a loop of current. We take some time to derive the magnetic fields due to circular current loop, which you will see applied in a couple different contexts in this class, and due to a long straight line current, which we will do again as an example of Ampere's law application. Finally, in the remaining time, we cover some science trivia about how basic SI units are defined. This is it for Biot-Savart's law. The Biot-Savart's law occupies a similar role in magnetostatics as the Coulomb's law did in electrostatics. It's a basic law that can help us develop intuition for the field and handle any distribution of extended source arrangements. But when it comes to deriving the useful field formulas, we will often use a different method that can make use of symmetry in dealing with highly symmetric source distributions. In electrostatics, that was Gauss's law, equivalent to the Coulomb's law, and in magnetostatics, this will be Ampere's law, which we will cover in the next lecture and is equivalent to the Biot-Savart's law. So in chapter 12, what you are looking at is the source of magnetic field. For the purpose of chapter 11, we kind of assumed you have a magnetic field. It comes from somewhere. Maybe it comes from a permanent magnet. Maybe it comes from something else. You just have the field. And we worked out what should be the interaction between that magnetic field and other things that interact with the magnetic field. And we went to the most fundamental interaction, which is the interaction between magnetic field and a moving charge. So we did that in chapter 11. Now, so in chapter 12, what we do now is address that question that we left open when we were doing chapter 11. Where does the magnetic field come from? This is where I want to point out, so, in a physics class, we don't often pay attention to the history of physics. We make terrible historians. We don't really care how something was discovered. We care more about what it is. But I wanted to shine some light on this discovery of the relationship between magnetic field and current because it's a quite complicated relationship. Many different smart people contributed to the discovery, and it's I think it's just good enough to just look at it and marvel at the fact that somehow people are able to make heads and tails of this complicated relationship. So for the discovery of the relationship between magnetic field and current, I actually have to go back to our previous chapter, chapter 11. When you look at section 11.1, magnetism and its historical discoveries, it talks about history of magnetism, and it starts from things that were known from ancient Greek times. So something like a compass needle is something that's been known since antiquity. And what we are going to point to is the modern discovery that looks at the interaction between this compass needle and electrical current. So in this section, there's a paragraph that talks about, here it is. Back in 1819, the Danish physicist Hans Ørsted, I think that's the pronunciation, if I'm wrong. Sorry, these a lot of European names. I'm gonna pronounce it like either it's English or German, knowing that that may be wrong. Those are the two languages that I know how to pronounce. So, Danish physicist Hans Ørsted was performing a lecture demonstration for some students and noticed that a compass needle moved whenever current flowed in a nearby wire. And I don't think it was a quite an accidental discovery as this paragraph makes it sound like, because I think there was some suspicion that there was a relationship between magnetic fields and electrical current. So I think he was actually looking for a relationship like this. It takes attention to detail to know this. So what I want to show is a lecture demo that reproduces what Ørsted might have observed, except in our setup, it's quite easy to observe because I have a purpose-made device that's designed to illustrate it. So let me show you the video and I'll introduce Biot-Savart Law. So this is a lecture demo that's meant to reproduce in some loosely connected way the discovery that Hans Ørsted made. So what you have here in the middle, that's a compass needle. So when I start running the video, you will see it behave like a compass needle. So as I turn this apparatus in one direction or the other, the compass needle, it continues mostly to point in the same direction. There's a little bit of friction between the support and the needle, so it does end up moving a little bit. But when I bring everything to rest, this needle kind of swings back and forth, where the equilibrium position is pointing towards the wall. So when I recorded this, the direction of the wall is the southward direction. So this blue needle is pointing to south. And now is the demonstration with electrical current. I turned on this apparatus. So it has a loop of current that the wires are not shown directly here, but there's a loop of current, and this light is indicating in what direction the current is flowing. So this is indicating the current should be flowing in counterclockwise direction. As soon as I turn up the dial, so this current needle moves from its zero position right now. So there's going to be current flowing in this wire, loop of wire, both here and the one in the back. And you will see the behavior of this needle change as more current begins to flow. So watch. So it almost looks like the needle is being held in that direction. And you can see that as I rotate the apparatus, that it's rotating with the apparatus. So whatever force is holding onto this compass needle, which we assume is magnetic force, it's associated with that, with the apparatus. That's the purpose of the rotating the apparatus, so that you can see there's something in the apparatus which contains no magnet, but has a current flowing in loops of wire, that something is producing a magnetic field. Now, what I'm going to do next is I'm going to reverse the direction of current and watch what happens. I reverse the direction of current. So the current, when I turn the dial so that the current begins to flow, the current will now flow in the clockwise direction. And remember what I said about this blue end of the compass needle pointing to south? Now, let's see what happens as I turn up the current. It reverses direction. It's going to swing back and forth quite a bit, so I just made it stop so that it doesn't swing back and forth so much. As I increase current, you can see that it looks like this is being held around this point. And as I move the apparatus, the needle rotates with the apparatus, indicating that there's a magnetic field that's fixed with how the apparatus is set up. And when I turn off the current, the needle goes back to the previous orientation, with the south end pointing towards the wall, which is in the southward direction. So that's the demo. This is illustrating what Ørsted's discovery was. And I think a compass needle is useful for visualizing the direction of magnetic field. So we're stepping back a little bit from what we talked about in chapter 11 about the magnetic force being V cross B. I think if we use this intuition for how the direction of compass needle is related to the direction of magnetic field. So this is an illustration of a bar magnet, which I hope you have some sense of familiarity to, and how the direction of the compass gives you a sense of the direction of magnetic field. You can almost imagine the compass as a kind of an arrow, or needle, or an arrow. So if you follow those arrows and trace out what the direction of magnetic field looks like here, magnetic field coming out of North Pole, magnetic field going into South Pole, and the in-between region just following these arrows, the kind of fields you see here, I hope that seems familiar. It's the dipole field that you have seen in electrostatic, and before electrostatics, field pattern that looks like this. This is something that you might have seen visualized in a high school physics class or science class with iron filings around the bar magnet, and I wanted to point to this to say, when you saw the compass needles pointing in different directions with that apparatus involving electrical current, the direction of compass needle is what indicates the direction of magnetic field. You can just directly associate it that way, and it'll be good enough for at least figuring out the direction of magnetic field. So let me sketch out what we saw with the apparatus. And once I draw the sketch, I think you can see how different it is from the electrostatic phenomena. So this is the illustration of, I'm just gonna put in quotes, Ørsted's experiment. I mean, I'm sure his experiment was in a different setup, but it's close enough how electrical current affects the affects the compass. It's good enough for that. So we have these two pictures. Let me imagine drawing a top-down view. So in the top-down view, in the first case, we had this orientation of compass. South end was pointed away from me, and north end was pointed towards me. And we had two loops of current. From a top-down view, those loops of current would look like this, and help us imagine the three-dimensional direction of current and everything. I can say, so the current was flowing counterclockwise. So as I look at it from the top, on the right side of the current, it should be coming towards me. And on the left-hand side of the current, it would be going away from me. And it's the same direction for both coils. So this is what we had in first case 1. So in that picture, somehow this arrangement of current somehow resulted in a magnetic field. So if my compass needle is oriented this way, the magnetic field must be pointed this way, in a rough sense, somewhere in the center region where the compass needle was. Okay, that's a case 1. Let me draw the picture for the case 2, because it's quite similar yet different. We reverse the direction of current. So as we are looking at it, instead of going counterclockwise, the current was going clockwise. So if we imagine looking at it from above, on the right hand side, the current was going away from us. So the direction of current was away or into the page here, and on the other side, it would be coming towards us. So that's describing the clockwise current that we established. Same for both coils. And what we saw was this compass needle was reversed in direction. The south end was now pointing towards us, not away from us. So we have south here and north here. And that direction of compass needle means our magnetic field was pointed away from us, as we are imagining standing on so this is the experimenter side, and we are imagining looking at it from above. Now, I want you to imagine what a comparable situation involving Coulomb's law would have looked like. So if you had a ring of charge here, and you had a ring of charge here, somewhere in the middle, the electric field due to these charges would have kind of balanced each other out. And somewhere in the middle, your electric field would have been zero. And in any case, in this hypothetical picture, thinking of similar arrangement involving electric charges, the one thing that you wouldn't have expected is for whatever field that's produced to have this kind of directional dependence. And looking at here, just to draw one more picture for case one. So this is the picture that we had for case one. We had a current that was flowing counterclockwise, and somewhere around here, we had a magnetic field that's pointing towards us. So we had a magnetic field that looks like this. It's not any kind of direction that we would have guessed. For an electric field in this setup, electric field would have maybe pointed somewhere towards like center directed direction. And what this is getting at is the rather complicated relationship between direction of moving charge and the other geometry considerations, and the direction of magnetic field. There are those three vectors involved, and their relative directions are not as simple as what we have said for electrostatics. With the Coulomb's law, the relationship between the different spatial orientations and direction of field, they were super simple. If you have a source of charge here and you are looking at that point, the direction that points to that point is my r hat vector, and my electric field pointed in that direction. This was what we saw with the Coulomb's law, and it was super simple. And this resulted in the Coulomb's law expression, which even in vector notation, we can state it in a kind of a simple way. Once we've written it down, it's not something that someone looks at and thinks, oh, that looks super complicated. Our Coulomb's law was that, well, Coulomb constant times the amount of charge divided by r squared, inverse of square law, times, for the direction, r hat vector. So kind of as simple as it can be. And with the magnetic field, what I hope this demonstration is showing is that the relationship is not going to be that simple. We cannot say that the magnetic field points in the direction of current. We can't even say somehow there's a simple relationship between the segment of this current carrying wire which generates the field and this r hat vector that points from the source to the point where you are establishing the magnetic field. And I will just leave it at here, which is that it took a lot of smart people doing very careful experiments to somehow figure out this relationship. And we are gifted with this fundamental relationship, which is as simple as it can be, given the complicated nature of the interaction. And this simplest as can be relationship is known as Biot-Savart Law. And it's got some pieces that are complicated. One is, let me write it down first and then we'll talk through it. So the infinitesimal amount of magnetic field that's generated by infinitesimal segment of current is given by, and I'm trying to remember the coefficient in front here. I think it's Coulomb constant divided by c squared times, and this is how it's usually written. I, indicating the amount of current in whatever circuit you are looking at, times, and we put the directional quantity in the segment, the line segment element of the wire, dl, cross r hat, divided by r squared. And on the all the complexity that I was describing, it's wrapped into this relationship between the direction of magnetic field and the direction of dl, which is line segment that points in the direction of current. And you see how this direction is changing as you go around this loop. Cross product with the r hat. So in this picture, our r hat for this segment here, this would be the r hat here. So that's the complicated directional relationship. And I think once it's written down, then it's not so surprising that this direction of this vector, and this vector are related through cross product, which means the direction of magnetic field is guaranteed to be, at least for a little segment, it's perpendicular to r hat vector, and it's perpendicular to the direction of current. And at least when you imagine that there's enough of a complexity that you can imagine how it'll work out. Detailed comparison between the Coulomb's law and the Biot-Savart law. And I think this comparison is useful for making sense of this complicated looking expression. Because one of the similarities I can note is Coulomb's law was an inverse square law. And even though this gets buried in detailed derivations from time to time, or most of the time, Biot-Savart's law also describes the magnetic field as an inverse square law. The reason this inverse square nature of magnetic field is not always apparent is it's kind of wrapped in here. Whenever you are calculating magnetic field, it has to come from an extended current distribution. There is no such a thing as a point current. So our application of Biot-Savart's law and other derivation of magnetic field will necessarily be complicated. It'll have to be more complicated than the electric field of a point charge was. So let me wrap up this video by showing how the directional information that's given here is consistent with what we experimentally observed. So let me use this picture to work out the right-hand rule for magnetic field inside this loop here. So I have the direction of current, which is going counterclockwise. So let me just take this point here. So for that point, my DL is pointing downward, and for r hat is pointing to the right. So I want to say DL cross r hat is pointing out of the screen. That's your perspective, and that is correct perspective. And that matches the direction of magnetic field that we see here. Now you might wonder, what about points on the other points along the loop? If I take this point here, for example, so DL points in that direction, and r hat points in this direction. let's just try it. So I want my right hand to be pointed kind of right and upward. Okay, so that's the direction of DL. And let me try to orient my hand so that I can bend my fingers in the direction of our head, which is the kind of leftward and up. So this is the orientation of my hand, that where direction of my thumb gives the direction of B. And yeah, it's still out of the screen. So as you go around counterclockwise direction, your hand is originally pointing in the direction of DL, and our head is pointing radially into the center, and direction of magnetic field points out of the screen. And in the case of case 2, your direction of our head remains the same, but your hand, instead of doing the counterclockwise thing, now it does the clockwise thing. So, so as your hand does a clockwise thing, if your DL points this way, the center is here, our head points this way, so your thumb points into the screen, and that's what you got with the magnetic field into the page. So yeah, that's introduction to Biot-Savart Law with its complicated looking expression. And to connect this to the other lecture, so this is something that I started doing based on a feedback from an experienced physics teacher, and he had advice for trying to continue using Coulomb constant past the initial introduction of Coulomb's law and the Gauss's law. A lot of textbooks will switch at some point from using Coulomb constant to the permittivity of free space. So Coulomb's law would be written like 1 over 4 pi epsilon naught q over r squared r hat. And this approach does make Gauss's law look simpler, and so I mean, there's a justification for it. Now, with this approach, when you get to Biot-Savart law, Biot-Savart would be written in this form. It would be written as mu naught over 4 pi times everything else, ideal cross r hat over r squared. So in this approach, where you switch to using permittivity of free space, you introduce this magnetic constant, which is called permeability of free space. And I guess when you look at here, the downside of using these separate constants is that it doesn't highlight as well the unified nature of electricity and magnetism, which is what we are getting to by the end of the semester. And in this approach of writing down this particular set of constants, I hope you look at this Coulomb constant and wonder, wasn't that an electric constant? Why is it doing it in an expression for magnetic field? Well, it belongs there for a very good reason that you will see by the end of the semester. And this is a new constant that I'm introducing. C here, it stands for speed of light. And as you hear it, I hope you wonder, what's light got to do with anything? There's no light involved here. Well, there is, and we'll get to it by the end of the semester. And that's why I'm switching to continuing to use Coulomb constant throughout the entire semester. I hope it'll highlight for you, it'll foreshadow for you some of the things that are coming up. All the sense of direction is placed on DL. And all these are magnitudes and constants. So whatever direction this DL cross R hat points in is the direction the contribution to the magnetic field will point in. So when you look at this here, all right, so DL, I guess I should draw it maybe bigger so that, let me actually take this DL and transpose it and draw it here so that I can have something to visually see. So this will be my DL, at least the direction-wise. Good. This is the same vector I had here, just drawn super tiny before. Okay. R hat vector, let me take this R hat, translate it, draw it here. So this is the direction of r hat. All right, now I have something to look at, apply my right-hand rule to figure out what the direction of dl cross r hat is. What's the direction of dl cross r hat? Yeah, into the board. So the contribution due to this little segment of wire to the magnetic field here is into the board. So this is the direction of my magnetic field. Let's go over these couple exercises, and I want to give you a little bit of time to try some of this on your own. Because this is the intuition building phase. So, when you come back to this in a couple of weeks, all of this should look simple, but I think it's important that we spend the time now to make sure that you have the correct intuition for this. So let me finish this example, and I want you to go through a similar exercise for these two geometries to figure out the magnetic field direction here. So let me do two more things here. So what we have done so far is figure out the contribution to the magnetic field at this point, due to this small segment, which means to have a sense of the overall direction of the magnetic field. Not just the dB, but I want to figure out the direction of the total magnetic field. What would I get if I add up all the contribution from nearby currents? So that's what I want you to imagine. So for this straight wire, as I look at different segments of the wire, which of these two vectors are changing? dl or r hat? R hat is changing, right? All right, so let's do a couple more points so that I have some sense of, is this dB continuing to point in the same direction, or is it going to start pointing in some different direction? So let's call this point 1, this is point 2, and call this point 3. So for these three different points, for point 2, so this is going to be my vector r hat 2. For point 3, this is going to be my vector r hat 3. So I want you guys to do this exercise in the 30 seconds or so. So what is the direction of the cross product dl cross r hat 2? And what is the direction of the cross product dl cross r hat 3? You might need to use your hand, unless you have the answer already. All right, so what is the dl cross r hat 2? Yeah, still into. So, r hat 2, it's like this vector except over this way. So dl cross r hat 2 is still into the board. And what about dl cross r hat 3? Yeah, still into the board. So the angle between these two are changing. So the magnitude of the cross product might be changing, but the direction of it's not changing. So when you add it all up, this direction is going to end up being the direction of the overall magnetic field. So at this particular point in space, magnetic field is pointing into the board. And if you try this exercise with any of the other points on this side of the wire, you will get the same answer. Magnetic field is pointing into the board. So, all right, let's do one more point just to confirm some geometric picture that you might have already. So let's pick a point here, up here. So I want to figure out what is the direction of magnetic field at this point. So you can do contribution from 1, 2, 3. Let me just do the contribution from 2 as an example. So the dl vector still doesn't change. That's sort of determined at the source. So the r hat 2 vector, because the point that I'm looking at is now different, this is going to be my r hat 2 vector. What's the direction of the magnetic field at this point? Yeah, dl cross r hat, it's out of the board. And when you try similar exercise with all the other points, so for every single point on this side of the board, you'll get, well, it's out of the board.
So, all right, so that's sort of the picture you get when you imagine individual points. And what I want you to do now, in a couple minutes or so, is sort of what that looks like three-dimensionally. So if you have a wire, and let's say end view, you are looking at the current coming towards you. In that case, well, the magnetic field in the space around that, what does that look like? So we gave the view gave direction of magnetic field for a side view, right? So I want you to think, imagine it three-dimensionally and imagine what that would look like if you are looking at the point of the wire coming towards you straight. And with those two combined, draw a perspective view. That's sort of a faithful three-dimensional or two-dimensional rendering of the three-dimensional thing. So this will probably take a minute or two. And when you're done, I want you to give it a try for a circular loop, like what the direction of magnetic field would look like. So let me give you a few minutes to work on that. I'll walk around where people are, and yeah. All right, it looks like everyone's done with the A. I mean, so either you already knew the answer or you're developing good intuition. So let me try to motion it in 3 dimensions. So this is what the magnetic field should look like. If this is the wire, then the magnetic field should look like it's going around. That's what you see here. So magnetic field, it's coming out of the board here. No, sorry, into the board here, coming out of the board here. And when you connect that direction, it would complete a circle. Yeah. So yeah. So if that's the sense of intuition you have, great. So illustrating it with a picture, it would look like. So the end view would look like you have some look coming out of the board. So you would have something that looks like this. And when you have a current that's current that's at this point in space, looking at Biot-Savart's law, if I simply drew a single circle, would that be accurate picture? As in, there's magnetic field here and no magnetic field farther away? No, right? There's magnetic field essentially at all space near this current. Once you have, it's like the same thing with electric charge. Once you have something that's generating the field in space, its entire vicinity is filled with a field. So if I were to draw the magnetic field lines following rules that were similar to the electric field lines, it would look something like this. Well, I'm not quite spacing it right, but if I'm spacing it out correctly, then it would look like it gets spaced out farther and farther as you go. So let me just draw, yeah. So where it's denser, it represents the fact that your magnetic field is stronger because of smaller r here. Okay? But if you draw a single circle, that's fine. In terms of indicating the direction, that's how it goes. And so in the perspective view here, it would look something like this. Circle that's going around like this. So you expect to have the same magnetic field all throughout along the length of the wire. This is probably a good point for me to introduce one of the shortcut right-hand rules that I mentioned was coming up. So for you to figure out this direction, you had to do this cross product, right? You had to figure out, okay, DL is coming out of the board. So look at this point. Then this is my R hat. So DL cross R hat, it's pointed downward. And you had to try that out for a few different points before you could figure out, oh, it's going in a circle, right? What I can tell you now is that there's a shortcut that you can use to figure out if you have a current flowing in one direction, then now you have some intuitive feel that the magnetic field is going in a circle around it. And there's a shortcut right-hand rule that'll tell you that sense in which it's going around. So this is, as I said last time, this is why I prefer the whole hand version, because it morphs naturally into this. So I use my right hand for the same reason as we talked about last time. So the way I orient my right hand is I orient it so that my thumb points in the direction of the current. So I orient it this way. So my thumb points in the direction of the current. Then the way my finger curls around is the direction that magnetic field curls around. So here, my thumb points out of the board. So my fingers curl around in the counterclockwise direction, and that's the direction of magnetic field. Okay. So it's a shortcut rule. It's and it's consistent with the basic rule that we reviewed last time. It sometimes makes it easier to quickly figure out the direction of magnetic field. Okay, so how many people are done with the circular loop already? Some people are. Let me give you a minute or so. So actually, this shortcut rule that we just covered will help you do this more quickly if you're just finishing up. Okay. So maybe about a minute, and we'll go over this. All right, everyone ready? Yeah. So let me use the shortcut rule. So using the shortcut rule, this is what I can do. I guess it's easier to do it in the end view. So I say, all right, on this end, the current is coming out of the board. So the magnetic field due to that current that's coming out of the board sort of loops around like this. So let me just draw a small circle here for now. And here, current is going into the board. So the magnetic field due to that loops around like this. Let me draw a small circle here for now. So the reason I'm drawing a small circle is I want to look at only parts of space that's mostly affected by this segment of wire, where I can kind of ignore the other thing. And if I do the same thing here, then it'll look like coming out of the board. So small circles like this, small circles like this. And if you imagine doing it for the rest of this loop, then small circles like this. Do you notice anything common with all these small circles of magnetic field? I'm not really coming. So from inside, so imagine I'm looking at the current on the back side of the loop. So current is going from right to left. So the magnetic field outside of the loop points downward. Magnetic field inside of the loop points upward. In fact, is that the description I can use for every one of these loops? Magnetic field outside points downward. Magnetic field inside points upward. So if you extend this picture, this is what it looks like. So here magnetic field is pointing up. Here it's still pointing up, still pointing up. Because they are all adding together in this region. There's nothing that's trying to make the magnetic field go downward. Out here, we'll do that later. So this current loop, we are going to use this example again later in the class. It's actually a model of a very basic magnetic object you have already seen, actually. But I want to use this to introduce the second shortcut rule that's sometimes useful. Because, remember what I said about current? That's the whole reason we had to have this. There's no such thing as a point current. Whenever you have current, it's going to be going over some space. So this actually illustrates the two most common ways you can have current where you look at some localized part of it. This is where you imagine it's an infinitely long straight wire, and you just look at a part of it. So there, the wire doesn't begin or end because it's infinitely long. Here, this is the other way where you have formed it into a loop. So here, wire doesn't begin or end anywhere because it's a loop. So that's where the shortcut rules apply to one of the two geometries. The first one applied to the straight geometry, so the right hand, thumb towards the current, magnetic field curls around. Here, what I'm hoping you're beginning to notice is that when you have a current that's going in a circle, then the magnetic field that's a result of the current that's going in a circle actually is kind of straight in one direction in a particular region. So this is the second shortcut right-hand rule. Once again, taking your right hand, this time what's curling is the current. So you orient your hand in such a way that your four fingers curl in the direction of the current. Then your thumb points in the direction of the magnetic field inside that loop of current. So here, so the way it goes, so it goes into the board, so it has to curl this way, and the thumb points up, and that is the direction of magnetic field. So the thing about these both of two shortcut rules is that they are based on the very basic fundamental rule that we reviewed last time. So it's a shortcut. If it makes sense to you, it helps you, great, use it. It'll shorten your problem solving time. But if it confuses you for some reason, then you can always rely on the very basic rule that we have covered from the beginning. Yeah. So it's for this presence of these two shortcut rules that I use the whole hand version. Because if you are used to using 3-finger version, then this doesn't change into the shortcut rules. So it's like, what do you do? Yeah. So these are the directions of magnetic field. I have some calculation examples I want you to go over, and I'll start out with the circular loop because this is the one that I feel confident that I can do it without any outside help. And so we'll start out with this one. So this is the magnetic field due to loop of current. So I want you to imagine a loop. Let me draw it in a couple different views. So the side view of this loop would be where, so it helps to have a physical object. So this is the loop I want you to imagine. So side view would be like this. So what I have to specify is at the top, is it going into the board or out of the board? Let's say at the top it's coming out of the board. And at the bottom, let's say it's going into the board. So that's the description of the loop. The side view doesn't look anything like a loop, so let me draw a perspective view so that it's easier to imagine. So this is the perspective view. At the top, it's still coming out of the board. At the bottom, it's still going into the board. So if you imagine this segment is behind, then this is going up, and this segment is coming down. Okay. So to find the magnetic field everywhere would actually be quite a bit of a challenge. That's more of an upper division level material. I'm not going to do that. But what I think I can do without any help from computers is I think I can calculate the magnetic field along the axis. So let me set up my coordinate system. Let's say this is my coordinate axis. X-axis goes in this direction. Y-axis goes that way. So Z-axis comes out of the board. But the one that's most important here is the X-axis. And the way, so this is the line that's going in the direction of the X-axis that's going through the center of the circle, center of the loop of radius R. And I think I can calculate the magnetic field at all points along this line. That I think is something I can do calculationally. So let me just describe a point here. Let me take a point here. So which will be from this plane of the loop, it will be located at a distance x from the plane of the loop. And we will use Biot-Savart Law to calculate the magnetic field at this point as a function of x, so it will be a magnetic field at all points. We proceeded with this calculation the similar way we did the electric field calculation using Coulomb's law. Remember that? That was a while ago. And when we did it, essentially the point of me doing it was to tell you this is not how you want to calculate electric field. You want to use Gauss's law. So this proceeds similarly. The only difference is, with the electric field, you could deal with a point charge. With the magnetic field, this is the simplest example I can give you. So, all right, so we'll go through it the same way we did it before. As in, we are going to first identify a segment of the loop that we are going to look at, see what kind of magnetic field it produces here, and go on from there. Now, normally, I would try to pick some generic portion of the ring, right? So that this can represent with some parameterization, let's see, from the y-axis, parameterization, angle phi, I can then describe the rest using this generic segment. For this one, I'm going to be a little bit more careful because there's going to be some complications. So let me pick this, the top segment. I can pick that without any loss of generality. Assume just whatever segment I picked, I rotated it to make it the top here. So, so I'm looking at the contribution to the magnetic field at this point due to a small segment of wire at the very top. From a small segment of wire at the very top. So, so on the perspective view is where I can indicate the length dl. Now, what is the direction of the wire segment dl? Is it within the plane? Is it out of the plane or into the plane? Like looking at the direction of the current that I have drawn. So out of the plane, right? Same direction as the current. So the dl here points outward or out of the plane. All right. The r in Biot-Savart Law, it stands for the distance between the section of the current that you are, or section of the wire that you are looking at and the point. So this is the distance r. Do we have enough information to write down what r is in terms of all the known quantities here? Yes? Pythagorean theorem, r, big R and x. So this distance is the square root of r squared plus x squared, and I'll be using that. All right, so to end this diagram, I need the direction of r hat. This is r hat. What direction is r hat pointing in? Sangmin? Straight in the positive x direction, or is it a combination of x and some other directions? Okay, which other direction? Motion for me, what direction it's generally going? Pointing up? No. Okay. So let me start from here. Tell me which point is the correct direction for r hat to be going. There, right? So, this is the direction for r hat. It's, it takes a while getting used to, but it is an intuitive direction. The r hat is the unit vector pointing from the source, whether it's a charge or current, from the source to the target point. So r hat points in that way. So let me draw a separate diagram that illustrates all these vectors so that my drawing here doesn't get clogged up. So all these vectors, dl, that's coming out of the board, and my r hat, that's pointing down this way. So what I would like to know is what is the direction of dl cross r hat? Is it in the plane of the board, or is it somewhere into or out? In the plane? Okay. So in the plane of the board, there are many directions it can point. Which direction is it pointing? Okay, perpendicular to r hat, that's good. So that means I have these two possible choices. Which one? 1 or 2? Yeah, that's where you have to use right hand rule. All right, yeah, so it's the 1, this one, right? So that's the direction for dl cross r hat. So let me draw that here. So dl cross r hat, it should point in a direction that looks like this. And I might, for clarity's sake, I might indicate that this is perpendicular, because that's how I'm trying to draw it. Okay? And in fact, this dl cross r hat, that is the direction of the magnetic field, or the small contribution to the magnetic field. So I'm going to replace this with just the dB. Okay? Now, here's the difficulty. Does this look like, one, is this in the direction that you intuitively thought the direction of magnetic field was? Like intuitively, what would you say the direction of magnetic field is at this point? Just straight along the axis, right? That's what we drew here. So that's what your intuition says. This is not in that direction, which must mean that the component that's perpendicular to the axis is somehow canceling out. So you need to make this argument that component that's perpendicular to the axis is going to go away when you add up all the contributions. So this is where you look for what other part of this loop will cancel out when you added the contribution to this. They will cancel out the perpendicular component and leave you only with the component along axis. And looking at here, I think I'm going to go with this. Everyone agrees? Yes? So on this perspective drawing, it would be this segment here. When you consider the contribution here, so R hat points in this direction. That's my R hat. DL points out of the board. So go through the same exercise. DL cross R hat. Oops. DL cross R hat. I'm not doing this right. So DL, oh no, sorry, DL is pointing into the board. Yeah, okay. DL cross R hat. Okay, so my thumb is pointing this way. So contribution to this portion is down here. This is the dB, and perpendicular to this. So you see the symmetry between the top and the bottom. So, this is the mirror image. And so I guess the last piece I need is I need to be able to argue that the magnitude of this is same as magnitude of this. As in, is everything here the same for both of them? Yeah, right? Current is the same. And R, you can go through, this is the same radius R, same X, so, so they are the same in magnitude. So when you add these two together, the resultant vector is going to go only along the axis. So once you figure that out, then for the rest of the calculation, you simply look at the X component of the magnetic field with the confidence that any Y or G component of magnetic field will simply cancel out. And if I was doing, picking this generic element, then what I imagine doing for this generic element is I imagine picking another generic element right across from that, and these two will cancel out in any component that's perpendicular. So I think I mentioned the name of this technique before. This is called pairwise cancellation, and it comes up a lot. It's a useful technique. There's a reason I didn't do this question the same way I did some of the electricity questions, where I simply write down unit vector representation and simply go ahead and do the integral. Because here it's beginning to get complicated. So it's worth going through this step to figure out, I only need the X component. That's the only component I'm going to worry about. Okay, so with that, I think I have everything I need to actually set up the actual calculation. So this is what I'm going to say. I'm going to say the magnitude of my magnetic field is going to be the sum or integral over all these small contributions added around the loop. And I'm only going to add up the contribution to the X component, because I'm going to say Y and G component, they're going to cancel out. So, all right, I have a law that tells me what this is. That's the Biot-Savart Law. So this is, once again, another reason magnetism is complicated. The very basic application of Biot-Savart Law involves an integral. So, all right, let me write this all out. So I'm still going to imagine integrating around the loop, but let me write all of that down. So it's mu naught I over 4 pi r. I'm going to take care to write down this r. So r squared, that's just the square root squared, r squared plus x squared. All right, so I took care of mu naught I 4 pi r squared. Okay, so I need to write the magnitude of dl cross r hat. DL and R hat, are they 90 degrees? Or are they, so DL is pointing this way, R hat is pointing this way. Are they 90 degrees or some other angle I need to be worried? 90 degrees, right? So that makes things nice for me, meaning that makes the magnitude of this simply magnitude of DL. Right? R hat is a unit vector, and the sine theta, it's just one. So it'll be just magnitude DL. And now I have to take care of this taking the x component portion. That's why I've been drawing this diagram so that I can figure out what the x component is. If I label this as my angle theta, then I can represent the x component. So this would be my dbx. I can represent my x component as the magnitude times cosine theta. So the easy impulse is to simply write in cosine theta here. But let me go through one more step so that I can actually express this integrand in terms of things I know, because theta is a new symbol I just introduced. So I want to re-express theta in terms of all these geometry quantities that I know. So does anyone remember this technique that we use? I think we've used it maybe once or twice in this class. Well, yeah, as I said, we used it once or twice. So this technique is called drawing the triangle. So I want to draw a triangle, draw the right triangle that has theta as one of its angles. And that'll help me figure out how to express cosine of theta in terms of other things I know. So here, the triangle that I know most about is actually this triangle. Right? I know both of its legs, and I know the hypotenuse. So the easiest thing to do is to locate theta somewhere in this triangle if that's possible. Now, would this be angle theta? When you look at it carefully, it should be no. Like even if you say this is theta, like they don't actually align. So, but this is theta, this is 90 degrees, which means this must be 90 degrees minus theta, which means actually this is theta. Good? So now that I have the triangle, cosine theta is the adjacent over the hypotenuse. So that's how I can write down cosine theta here. So this would be times adjacent, capital R, over the hypotenuse, square root of r squared plus x squared. So this is the cosine theta that's taking the x component. Yeah. It's forgetting that taking the component is a really easy mistake to make. I can't tell you guys how many, like when I was taking the upper division electrodynamics, like I do all the calculations, I thought I did it correctly, and the answer's wrong. It turns out I forgot this component. Like that's what happens. So, all right, let's try to finish this calculation. I need to do one more thing. So I'm going to imagine integrating around the loop. So I have to parameterize this integral. I have to express it in terms of some coordinate variable. So I kind of started doing that here because I was using phi as a coordinate variable I can use to address this portion and then go all the way around the 2 pi to go around the whole loop. So it's a question of how do I re-express this dl in terms of phi? Anybody here know the answer already? Yeah, RD phi. The way to look at it is this dl is the arc length. So how do you express arc length in terms of angle? Well, radius of the circle times the small change in angle. Good, so that's it. So I'm going to rewrite this as r d phi. All right, and the integral for the loop would be phi going from 0 to 2 pi. So let me write all of that out here. And I'm going to skip one step and sort of factor out in front anything that doesn't depend on phi. Okay? So this whole thing is equal to, let me pull out all the constants, mu naught over 4 pi. Does I depend on the angle phi? No, it's the same current, so let me pull that out. Does either r or x depend on phi? when you look at this here. Yeah, it doesn't depend. And here's where I was careful to use two different letters for two different angles. R and X are related to theta, but theta is not what we are integrating over. This is what we are integrating over. So let me pull out this. Actually, I'm going to combine this into one single expression. So it's r squared plus x squared raised to the power of 3/2. 2/2 plus 1/2. All right, I took care of this. Oh, I have this r and this r here. We just said r doesn't depend on phi, so I can factor out r squared as well. Did I factor out everything? Yeah, well, I did say this was the easiest example. So the integral is integral of d phi, where phi goes from 0 to 2 pi. So I did tell you this was the simplest example. So the integral here does turn out to be simple. All this is simply equal to 2 pi. So it's like taking this, multiply by 2 pi. That'll give you the answer. So let me just write it out. 2 pi cancels out some of this 4 pi. And you end up with mu naught I r squared over 2 r squared plus x squared 3/2. So this is the magnetic field due to a loop of current along axis. So this is along the axis where x can be, the x is the distance from the axis. Some features to note. So when x is equal to 0, this becomes a simple expression involving just a constant and r. If x is equal to 0, then this simplifies down to mu naught I over r squared. It gets canceled out by r to the 3rd power. So it becomes 2r. And so this is a limiting case where x is equal to 0. Does this expression make sense? That if you have a loop, it's carrying some current, and if you make the loop larger, then the magnetic field at the center would become smaller. That makes sense, right? That's the inverse square law portion. Now, it doesn't look like a distance squared because of this complicated integral you had to do. But it's still in the correct direction. If the loop is larger, so you're at a farther distance, magnetic field is smaller. So that's one way. And the other way you can make sense of it is, let's say you keep the r the same, but you get very, very far away in the x direction. Then how does this magnetic field change as a function of x? What is it proportional to? Is it proportional to 1 over x, 1 over x squared, 1 over x to the 3rd power? So I have x squared, taking square root, and then raising it to the 3rd power. So it's proportional to 1 over x to the 3rd power, right? And so this is how a dipole field looks like very far away. So this is the dipole field distance dependence. If you do this kind of calculation with the electric dipole, that's what you would have seen. That with some two charges separated by some distance, if you look at electric field very far away, the electric field would go as 1 over x to the cubed. So what you are seeing with this magnetic loop is that the magnetic field due to a loop of current looks like something that would be due to a dipole. And what that means is that, so we were asking this question earlier. So you guys are all used to dealing with these permanent magnetic dipoles. But we kept saying this is not an elementary object. Like it's too complex for us to consider. And that's why we were going into the description how magnetic field can be generated by something that's elementary as flowing charge. And what we are seeing here is that when you get the charges to flow in a loop, then those charges flowing in a loop produces a field that looks like a dipole field. And in fact, if I drew all these field lines into some larger space, these will look like a dipole field. So this current loop is the the very basic way you can model magnetic dipoles. Now, as I said on Monday, it does get complicated. The whole ferromagnetism, paramagnetism, diamagnetism, it involves quantum mechanics, and we are not going to get into that. But if we want to model it in terms of something fundamental like a current, then we can say, well, wherever you have magnetic dipole, there must be some kind of current loop that we can imagine that's producing that dipole field. Okay? So yeah, so that's the simplest example. As I said, it's pretty simple. The integral that I was dreading turns out to be just the multiplication by 2 pi. I think it's doable, but at some point I'm going to need help from Wolfram alpha. So let me set up the situation here. So this will be for magnetic field due to, let's say, long line of current. And what I'm going to say is that I have a long line of wire that's carrying current. And at least to set up the calculation, I will say that I'm considering some length. So at least to set up the calculation, I will say I'm considering some length L. But what I'm going to do later in the calculation is I'm going to let L go to infinity, to say it's an infinitely long wire. So it's going to be carrying current I. Let's have it pointing up. And I'm interested in the magnetic field due to this line of current at a particular point in space. So I'm going to illustrate that point with some parameters so that that point actually can represent any point in the space around the wire. So I'll say, let me make things easy for me. I'm going to take the midpoint of this wire where, let me set up the axis. So this will be my axis, x, y. So midpoint where y is equal to 0. And I want to calculate the magnetic field at a point somewhere out here, at a distance x from the wire. So the coordinate for this would be something like x, 0, 0. All right. So we do the same thing as last time. We last several times. So we have an extended distribution of source of the field. So way before, it was electric field. And just what we are looking at today, it was magnetic field. And for all those, the basic procedure is the same. We have a law. Let me write down the law that I erased. So we have a law, Biot-Savart Law, that tells me how I can deal with a small segment of the wire, I dl. And it tells me how to calculate the small contribution to magnetic field due to this small segment. But it doesn't tell me the total magnetic field due to any large section of the wire. So what I do is take this, imagine breaking it up into parts. So I am going to consider a small segment of wire here. I have to think of the parameters. So let's say this is located at some coordinate y. And it has small length, dl, so dl, which is a vector. So this is sort of my representation of dl. I'll draw it larger later when I need to figure out vector directions. So here's the dl that's in Biot-Savart Law. I need to figure out r. That's also in the Biot-Savart Law. So r is the vector from the point source, kinda, to a place where I want to calculate the magnetic field. So this distance, this entire distance will be r. And my r hat vector is the vector pointing from here in that direction. This is my r hat vector. It's kind of hard to see all these vectors cramped into that tiny space, so let me draw a bigger one here. So just using this dot to anchor all the vectors, my dl vector points up. This is my dl. And my r hat vector goes in this direction. This is my r hat. Good? Yes. Okay, so this is a two-step process like the last time. So we first figure out the direction of magnetic field, and then I guess go from there. So the direction of magnetic field at that point, dl cross r hat into the board. Seems way too simple. All right, into the board. So that's a dl cross r hat, so that must be the direction of dB. All right, so what that's saying is xy, so g is out of the board. So dB is going in the direction of minus g hat. That does sound simple. Well, let's see if there's something we are forgetting. What if we picked some different point along the wire? Are they all just pointing into the board? All right. If everyone's agreeing, then I guess we can just continue on with that. So let's say we are now trying to find the magnetic field. So the magnetic field would be B, will be the integral of this dB along this line of current. So I write down what this dB is. Mu naught, so all the constants, mu naught over 4 pi I dl. Well, dl looks like dy, right? Yes? Okay, I dy as a dy times, I guess, y hat. So this is my dl vector. Good. Cross r hat divided by r squared. Yeah?
So you can say that dl equals dy times y hat?
Yeah, I mean, so here I want to say my dl is equal to, so, I need two things, right? Magnitude and direction. So magnitude will be dy, the infinitesimal thing along the y direction. So the direction is y hat. That sounds correct to everyone, right? So dy y hat. All right, what is my r? So, r here is a new symbol I introduced that's an unknown quantity for the problem, right? So I have to express this r in terms of something I know. All right, square root of x squared plus y squared. That seems right. So let's say I plug that in here. So I end up with integral of a line mu naught over 4 pi I dy y hat cross r hat over x squared plus y squared. I square it, so square root goes away. All right, what do you do from here? Pull constants out. I probably should be more specific about how I'm going to do this integral. Because so far I have been, this is a symbolic notation. It's just a reminder to myself that the object that I'm going to integrate over. I have to actually specify at some point how I'm going to do this integral, right? So when you do integral over something like this, it's always over some coordinate variable, x, y, z. So what coordinate variable am I integrating over here? Yeah, the length, which is along y. So the coordinate variable here would be y. So you would say it's y from minus L over 2 to L over 2. Good? So, Kevin said pull out the constants. Once you figured out your the variable you're integrating over, that's when you know, okay, what is my constant, what is not. In fact, I have this dy here, which conveniently says that that's my variable of integration. So I have this y hat here, x. All right, that's so for each of the quantities, tell me if I can pull it out or not. Can I pull out mu naught? 4 pi I dy. I'm assuming no. Y hat. Okay, r hat. How many say you can pull out R hat? I heard some yes. How many people say we cannot pull out R hat? Yeah, so this is the part where you have to be careful. So this is where it's really worth the trouble to draw the diagram for a couple different positions. So I drew one here, magnetic field points in. Well, let me just try one more here. Let's say I'm looking at this one here. Then as long as you're looking at the expression R, well, you'll get the same expression for R, square root of x squared plus y squared. But when you draw R hat, that's when you should realize, oh, that's not pointing in the same direction my other R hat was pointing. And in fact, this is one of the reasons that when I did the integrals for the electric field, I always did it in the Cartesian system. The reason is the Cartesian unit vectors x hat, y hat, z hat, they are really nice in integrals because they're all constants, they don't ever change, you can always pull them out. That's not true of polar unit vectors like r hat, theta hat, and phi hat, sorry, that's a spherical. But those unit vectors, they are nasty. They are functions of their position. So they are always going to depend on what point in space are you looking at. So this r hat vector here, it's a function of x and y. So you cannot pull that out. And in fact, this you cannot also pull out either because this one actually has y. So you would have seen that you cannot pull it out. So this is where I would actually take a step back. And before writing down this expression, sort of pre-simplify some of the expressions here. In fact, when I began this calculation, it looked like I was going to do the same thing I did with this electric field, right? Write things down in unit vector notation and work it out that way. I'll tell you now that with the magnetic field, I'm never going to do it that way. It all comes down to that this cross product is complicated enough that I don't really trust myself to do the calculation correctly unless I work out this cross product very carefully each time. So, when you look at this calculation, so I keep saying, oh, it's in the same direction of dV every single time. But is it true that dV did not change as I consider different points along the wire? So, one part changes because this R is changing, right? But is there another part that's changing as you consider different points along the wire?
The value for y is changing? The value for the y is changing?
Yeah, the value for y is changing, which is why I'm recognizing that this distance r is going to be changing. And that's all already written into my expression. But there's one more thing that changes that's kind of hidden. Unless you consider the cross product very carefully, this cross product very carefully, which we did in this diagram here. So which aspect of this diagram is changing as you consider different points along the wire? R hat is changing, right? This was the R hat for this. Let me do them in color so that I don't confuse them. So this is the R hat for this position. For the ones that are drawn in red, sorry, wrong choice of colors. The red, it's going to be, R hat is going to be in this direction, which means this angle here, called that theta, it's a function of position. So when you write out dl cross r hat, remember the full expression for the magnitude of this is dl times, well, r hat is a unit vector, so no length there, times sine theta. So there's this something that looks like a component again. It's not an actual component in the sense that magnetic field was pointing in the same direction, but there's going to be this sine theta that you still have to worry about. So we should work it out separately And when we write down our integral properly the second time, I should write this in at the very beginning so that there's no chance of me forgetting it and doing something wrong. Good. So let's look at this geometry. It's going to take a little more effort to drawing the triangle, maybe. So let me transfer this theta over to here. I guess it's this theta that I'm looking at, right? Oh, I think I already have the triangle. It's this triangle. Right? That's a right triangle that has theta as one of its angles. It has, I know, two sides. So, well, the side here, this is y. Side here, that's x. I know the hypotenuse. So just copying it over here, this is the triangle that I'm looking at. Theta, y, x, square root of x squared plus y squared. So sine theta, that's going to be opposite over hypotenuse. So I have to write that in. That sine theta is equal to x over square root of x squared plus y squared. Good. So let me start this over so that I'm writing down an expression that I know how to integrate, even if I don't know how to do the final integral. So when I look at my magnetic field, I'm going to start out with the acknowledgement that I know the direction of my magnetic field here. It's going to go in the minus g direction. So let me just simplify it that way first. So minus g hat, I took care of the direction. And the rest that I'm taking care of is the magnitude of the magnetic field B. That's the only thing I want to deal with in the integral. Because if I try to, doing the unit vector notation and trying to handle everything all in one shot, you can do it for simple situations like electric field. They are simple and intuitive. If you make mistakes, you will figure that out. Magnetism is not all that intuitive. So I separated out this way. Now let me try to figure out B. The magnitude of B will be, well, this integral here. So I guess I can write this much. So it's going to be integral. So all of this was fine. So I'll go y going from minus L over 2 to L over 2. All the constants I wrote down were fine. Mu naught I 4 pi. Mu naught I over 4 pi times. And it's the rest of the material here that I need to spend a little more attention on. So let me write it down in terms of these symbols that we figured out first. So it's going to be dl sine theta over r squared that I can write down using this. X squared plus y squared. Okay. And in fact, I guess I can get one step further with the same expression. So this dl sine theta for this particular geometry, it's going to be dy sine theta. Right? So let me just replace this L with a y. dy sine theta. So, all right, so I need to write out what sine theta is before I can do this whole integral. So now let me write down this one more equal sign. And I'm going to combine two steps and just factor out all the constants out of the integral so that I don't have to do it again second time. Mu naught I over 4 pi integral from y equals minus L over 2 to L over 2. And I have to write down dy, that's my variable of integration. I have to write down sine theta. I figured it out earlier. There it is. So let me copy that down. X over this. In fact, the square root of x squared plus y squared, that's going to multiply to this. So let me combine that as I'm writing it down. So it'll be x over x squared plus y squared raised to the power of 3/2. All right, so everything outside here is constant. I guess there are some constants still remaining here, but I think I can deal with that. Anybody here know how to do this integral?
Wolfram nothing.
Thank you. Yes, that is the correct answer. So, this is where I wish this was y, not x. If this was y, I could have done it with the u substitution. As it is, the proper way to do it by hand is trig substitution. I'm not going to spend class time for that, so let me use Wolfram alpha. So let's see, are those figures going to be in the way? Hopefully not. Okay, so I'm going to say integrate. And so this is the reason I pulled out some of the constants so that I can write down this. So I'll say x divided by x squared plus y squared raised to the power of 3/2. Okay, close the parenthesis. I guess I can say one more thing. From y equals minus L over 2 to y equals L over 2. This will also tell Wolfram alpha that y is my integration of variable, I hope. Wolfram alpha usually tells you how it interpreted your input. So you should check it to make sure it correctly understood what you're asking. So yeah, x, yeah, this is what I wrote down there, dy. And it says, so that's the integral for some conditions. Well, x is not equal to 0. Sounds good. I'm not going to go right on top of the wire. And for L, I wasn't even thinking that my L was a complex number. But so, this is one thing Wolfram alpha and mathematical always does. It assumes all your parameters are way more general than what you usually assume they are. So, but this matches is what I was thinking L was. L was a real positive number. All right, so this is my antiderivative. So let me use that and say B is equal to mu naught I 4 pi times, let me factor out, wait, it's not just the antiderivative. Plugged in these limits of integration already. So it's just this. So it's all of this times 2L over x square root of L squared plus x squared. And that's it. That's the expression for the magnitude of magnetic field pointing into the board. And so yeah, that's the expression. And I will just say one more thing. So in the limit where L goes to infinity, this is what happens. This becomes essentially L. So this will cancel out with this L here. So in the limit that L goes to infinity, you get B is equal to mu naught I, 2 cancels that, over 2 pi x. And we are going to point this out later, especially as we do Ampere's law. This begins to look very similar to magnitude of electric field due to a long line of charge. And we are going to bring attention to that similarity later. So okay, this was a review of what we covered the last time. Let me go over one thing that we didn't quite have time to go over last time. And I think it's a useful exercise, both as just a background in scientific knowledge or cultural things or whatever, and just to give you a sense of scale. Does anybody here know how the SI units, basic units in SI units are defined? This is sort of a trivia question. Does anybody here know how a kilogram is defined? There's an object. I mean, so, kilogram represents amount of mass. So when I talk about how is it defined, it's a question of how does NIST, National Institute of Standards and Technology, defines it. And they work with other international standards organizations. And when they define a standard in a particular way, it's a question of how precisely can you measure it. So as Kevin was saying, kilogram is defined by that's the only remaining standard left that's defined by an object. Kilogram is defined by a kilogram prototype. I don't know what it's called. It's stored somewhere in France. It never sees the light of the day because light could cause some chemical reaction that will make it lighter or something. It never gets taken out of the vault or ever because dust could fall on it and change its mass. So what they do is they make copies of the kilogram mass and send it around to other countries. There's a American copy that's kept in US somewhere, probably in some NIST institution, and they make copies and they get sent around. That's how they define the kilogram standard, which is gonna change soon, by the way. They're gonna define it based on some atomic constant or whatever. Anybody here know how meter and seconds are defined? Once again, this is trivia question. Unless you are science geek, you wouldn't know this. Anybody? Well, I think it's easier to know how seconds are defined. Anybody here know how seconds are defined? No? Okay, I'll just tell you. It's defined by a cesium clock. There's a very precise, I don't know. Let me just Google search so that you know I'm not making stuff up. Cesium clock second definition. So you can look it up somewhere. Second, I guess I could have just gone there. Look, on your own time, look at the, let's see, based on cesium. So that's the most, so the way they, even though the idea of second hasn't changed for a very long time, how we measure second has changed. Because it was based on daily cycle initially, but that's not very precise. And so over time, and this is the current most precise way of measuring time. So we define second this way. It's this weird set of numbers. Well, it's so that we don't have to change our common sense definition of second. But how we measure second for reference purposes, this is how it's defined. It's defined based on some energy levels of atomic clock. Energy level of a cesium atom, which is what dictates how the atomic clock operates. And there are many things in the world that we can measure to this many significant figures. This says 10 significant figures, right? And most of the times when you're writing down 10 significant figures, you are being ridiculous. This is an exception. That's where you actually do have 10 significant figures. So, a part in a billion. So that's how seconds are defined. Anybody here know how meter is defined? Length? Like, what defines a length of 1 meter? Like, I wouldn't define it based on this meter stick. It's not very precise. I cannot measure this to a part in a billion precision. Or if I did, it would change every time I touch it. So, or if temperature changes, it would change. Anybody here knows how meter is defined? Oh, nobody here knows? Never mind. There's one constant of nature that is known, is it just the one? Yeah, it might be the only one. There's one constant of nature that is actually given with an infinite number of significant figures. It's because we no longer measure this constant. We use this constant to define a meter. Anybody know which constant I'm talking about? Chris? Yeah, it's speed of light. We used to measure speed of light, but at some point people figured out, okay, the most precise way we can define length is to say this speed of light. So let me, once again, you can read it on your own later, but you can, let's see, there should be something down here somewhere. So it would be, speed of light in vacuum. So defining speed of light as an explicit constant. So it's a pretty recent thing. I guess, yeah. So speed of light is defined to be exactly this value. So you can imagine there's the 0.00000. So it has infinite, it's an exact value. And so taking this as exact, we define meter based on this and our definition of time. Yeah? So those are the 3 basic SI units that you have known since physics 4a that's being defined the way we humans define it. Because within our limits of our technology, that's the most precise way we can imagine doing those measurements. And the kilogram is going to be eventually redefined by defining another constant, Planck's constant, the way we did it for speed of light. That's going to happen in the next few years. So here's a question. There's one more unit remaining in SI unit system that we haven't discussed how to define it. Anybody have an idea which unit I'm talking about? There's one unit remaining. So you guys know the distinction between basic units and derived unit? Yes? Newton, is it a basic unit or derived unit? Derived unit. Newton is kilogram times meter per second squared. What about joule? Derived unit, it's meter times Newton. So having defined the kilogram, meter, and seconds, there are many other units you have seen that we can derive. You can derive Pascal, Newton per meter squared. But so it doesn't have to be this way, but we made this choice in SI unit system. There's one more unit that you have to define as a basic unit. Matthew? What unit do we have to define as a basic unit? Because you cannot derive it from kilogram, meters, or seconds. I thought you were saying something. Oh, okay. Never mind. So,
Is it Coulomb?
yeah, Coulomb. So that's the unit of electric charge you have seen in this class. So, once again, this is sort of a science trivia. So, it's a definition of Coulomb, because there's no way to derive Coulomb from other basic units. But as I keep saying this several times, to define all the physical quantities, you actually only need 3 basic units. Coulomb is kind of, it's not fundamentally necessary. But in the SI unit system, we made a choice to make this its own unit. So what we actually can do is we can come up with a physical situation and use the physical situation to define Coulomb. So now, so what that means is it's going to be based on measurement of force. So, so hypothetically, we could do it this way. We could say, I don't have. So we could say, Coulomb is defined by, amount of charge. You have to put on these 2 point charges, separate them by 1 meter, and then you should measure force of some number of newtons. That amount of charge is a Coulomb. You could define it that way, but we don't do it that way. It comes down to, it's difficult to see how many charges I'm putting on a object in a way that's independent of the force it's exerting. It kind of becomes circular. So you guys did the Van de Graaff generator lab, right? And the way you figured out how many coulombs were here was, or on the pith ball, was you measure the force, essentially. So when you're defining this unit, you have to try to think of a way, what is most feasible way of doing this? Not simply what can you imagine up in your head. So in an experiment involving electricity, it turns out what you can measure fairly easily is voltage. It's what you see on this power supply. It measures voltage and it measures current. Those are the 2 things that can be measured precisely and be established fairly well. So this is the way Ampere is defined. So the way Ampere is sorry, I skipped a step. This is the way Coulomb is defined. In the SI unit system, they don't actually try to define Coulomb. The way they do it is they define Coulomb by defining Ampere. How is Ampere related to Coulomb? What kind of quantity is Ampere describing? Yeah, coulombs per second. This is 1 coulomb per second. Ampere measures current. So current is measured in charge per second. So Coulomb is defined implicitly by defining Ampere instead of Coulomb. And this is the physical situation that defines Ampere. The physical situation that defines Ampere is this. So you have 2 parallel wires, and let's say they are separated by 1 meter. And experimentally, you can cause 1 ampere of current to flow. And let's say 1 ampere of current flowing on this other wire also. Then there's going to be a force between these two wires that are both carrying current. Why is there a force between two wires? Like if there was no current and I have two copper wires 1 meter apart from each other, should there be any force between them? No, I have net charge 0, so no electric force. There's no reason for there to be any force. So once the current flows, why is there a force between them? So there's a magnetic field involved, but I don't really want to describe it in the sense of they are both generating magnetic field, because I look at what generates magnetic field, that's a current, and I want to look at how is magnetic force exerted. Magnetic field does not exert a force on another magnetic field, because sort of field is a property of space. So what's the step you go through? So let's say this wire is generating magnetic field. How does that field exert a force on this wire? Is there an expression that we covered that actually we didn't write down there that describes the force due to a magnetic? So let's do a magnetic field first. Let's go through step by step. So I'm looking at this wire 1 as generating the magnetic field. So what's the direction of magnetic field due to this wire? Sort of goes around this wire, right? So if I draw it in a perspective view, it would look something like this. Or if I'm drawing in a side view, it would look like, all right, on this side, it's coming out of the board. On this side, it's going into the board, right? And the magnitude is going to change depending on distance. At the location of this wire here, there will be magnetic field going into the board due to this current. Okay. So what's the equation that tells you how this magnetic field is exerting force on this current carrying wire? Anybody remember the formula? It's equivalent to this, but since I don't really have velocity or charge, it has to be rewritten in terms of quantities I do have access to here. Current and the length of the wire. Yeah, so this was one of the expressions I wrote down earlier. So magnetic force on wire would be amount of current times L cross B. So the direction the wire's current is flowing in, cross product with a B. And it can be derived from this. Your textbook doesn't read it if you're interested. But this is one of the formulas that's useful to know. So it's this relationship that results in a force on this wire. Now, can someone tell me the direction of the force on this wire? Is it attractive or repulsive? Well, force between two wires. Is it attractive or repulsive? How many say attractive? How many say repulsive? Yeah, so this is where you have to be careful and go through the rules, right-hand rule. So I know the direction of magnetic field here. So into the board. So, I know. My hand shouldn't point in the direction of magnetic field. It should point in the direction of the wire. Yeah. So once again, you have to be careful with the right-hand rule. It doesn't matter which vector you point to first. So I'm going to make sure that my hand first points in the direction of current. And I orient it in a way that I can bend it in the direction of magnetic field. IL cross B, it's to the left. So the magnetic force on this wire is pointing to the left. So, yeah. So that's the result you get. When you have two current flowing in parallel, going in parallel direction, there's going to be an attractive force on this wire. And so you get the result by applying these rules. If you are remembering, some of the rules that we are using earlier, likes repel and opposites attract, don't use that with magnetism. I mean, I know it works with magnetic poles and whatnot, but as I keep saying, magnetism is complicated. Always go through the rules that you have been told until you develop enough familiarity that you know what the answer is before you do calculations. So, all right, so there's going to be an attractive force. Now, what if I changed my description around? Here, I said wire 1 generates magnetic field, and wire 2 feels that force. Would this answer here change if I switch it around? Say it's wire 2 that's generating the magnetic field, and it's wire 1 that's feeling the magnetic force. Would it change? Yeah, it should still feel attractive force. So we can go through it quickly. Current going here. So here, the magnetic field due to wire 2 is pointing out of the board, right? So making sure I do this correctly. IL cross B. So the force due to this magnetic force is still attractive. So I hope this is this reminds you of what we did with the Coulomb's law. So when we go through the device of field, it doesn't matter which of the two objects you say is generating the field and which one the field is acting on. And so all of this makes this whole situation consistent with the Newton's third law. This is the, let's say, action force, and this is the reaction force. Okay? So this is the situation, and I just want to go through a calculation to look at how this Ampere is defined and what the number looks like. So this is the number that I would want to calculate. What is the force between two wires carrying 1 ampere of current? So force between 1 and 2. If I simply say force, it's going to be infinite. Everyone here says why it's going to be infinite? You look at this relationship here, IL cross B. Is anything here infinite? Yeah, L. If it's an infinitely long wire, then it's going to be infinite. So I really say force between 1 and 2 per length. So let's say per 1 meter of length. So what we are going to calculate is Newton per meter. So force density or whatever. I don't think that's the right word. So let's just do the calculation. So this is the formula I'm going to use. So what I need to write down is, so this is going to equal current I times length L cross B. And let's just simplify this a little bit. So, L cross B, it's going to be LB sine theta. Anybody here know what the sine theta in this particular geometry will be? 1, right? Theta is 90 degrees. The current goes this way, magnetic field is 90 degrees to it. So, all right, so if we are looking at the magnitude, this is simply going to be current times the length times the magnetic field, which we derived over here. Good? So let me write it down. Magnetic field will be mu naught over 2 pi, mu naught I over 2 pi r. And for the per 1 meter of length, we are going to be dividing this by L. So it's the force per length that we are looking at. So L cancels out. I don't even have to plug in L, which is good. So let's just work out an expression and just plug in all the numbers and see how much force we are talking about. All of this sort of sounds like it's a standard amount of quantity, right? 1 ampere, it's not an excessively large or small amount of current. 1 meter, it's this much distance. I guess it's maybe a little bit too far. It's farther away than usual side, but it's, it's a amount of quantity that you can imagine. So let's see how much force we are talking about when we are dealing with that situation. So I have I squared mu naught. Okay, so let me write mu naught over 2 pi times I squared over r. And mu naught is actually one physical constant that I don't have to look up. I have it memorized. This is how I have it memorized. Mu naught is equal to 4 pi times 10 to minus 7 times some units that we are going to figure it out later. So that's a mu naught. It's a, yeah, I just have it memorized. Let's plug in the numbers and see. So, and then in the process, we'll also figure out what this unit should be. So the numbers here is mu naught, or 4 pi times 10 to minus 7 times some unit divided by 2 pi times current. We said it was 1 ampere. So 1 ampere squared divided by the distance. We said that was a meter, 1 meter. Oh, that seems like easy thing to work out. So let me work it out and write it down. This is equal to, so 2 pi cancels a lot of this. So I end up with a 2. 2 times 10 to minus 7, 1 squared divided by 1. So it's some unit of whatever this is times ampere squared per meter. The units that we are looking at, what should this be equal to? What quantity are we calculating? Okay, it's related to force, but it's not just the force, because we said if you're doing force, we would get infinite number. So what do we do to the force? Yeah, force per meter. So the unit here better end up being Newton per meter. So, that gives us a unit for mu naught. So unit for mu naught is going to be, I'm trying to stare at it and make the units come out right. It better be Newton per ampere squared, if I didn't make any mistakes. So this should be Newton per ampere squared. I haven't done this before, so let's just make sure that I didn't make any mistakes. This is how I would check that I didn't make a mistake. I'm going to look up what mu naught is on Wolfram alpha. Because Wolfram alpha, it's unit aware. It knows units of different things. So the mu naught has 2 different names. One name you can use to call it is magnetic constant. Let me use the old-fashioned term, permeability of free space. That's the old-fashioned term for mu naught. But a lot of people call it magnetic constant these days. So that's mu naught. Oh yeah, I was right. It's Newton per ampere squared, and as I said, it's when you work out this, it just should be 4 pi times 10 to minus whatever. So all right, that's mu naught. This is how ampere is defined. It's defined this way. If you have 2 wires carrying 1 ampere or ampere is defined as, ampere is such an amount of current that if 2 wires carry that amount of current and they are separated by 1 meter, then the force per length of the wire would be this much, 0.2 micronewton per meter. Does it sound like a lot of force? Well, it's a very tiny force. So that's why you have seen me, when I do the magnetism demos, I have to put out as much current as I can. This has a maximum of 3 ampere. That's what I put out. And even then, all you have seen is this wire just to move a little bit. So I think that's why a lot of people can have this impression that magnetism as a force is weaker than electric force. And to some degree, that's true, because it takes a lot of current to get some significant amount of force. But what I want to tell you is that the magnetism and electricity, they are related. So the intrinsic strength of both of them are actually comparable.